you want to remember one slide, this is it. So I'm a big fan of putting the message up really early in the whole talk. So if you can't remember anything else, but what this is I'm going to show an example of a highly parallelizable symbolic regression system. If you don't know what symbolic regression is, you'll find out. And an application in DFT that shows you can do symbolic regression on a problem that really matters, and you can get something that actually works. So that's the point of all of this. Now, I don't usually do like the agenda, like what I'm going to talk about slide, but I'm doing it for a particular reason here. So I'm going to explain what symbolic regression is, what this approach is, how it works. Then I'm going to go into more DFT details, how we set up the problem for a DFT functional. Then I'm going to show how the result works, or how the system actually worked, and then delve into the functional itself, why it's interesting, how it's different than the functional that it's sort of in the same family of. And last, I'm going to talk a little bit more about what I think this means, especially in this concept of emergence and learning concepts. Now, the reason I'm doing this agenda is the odd number ones here will be more accessible. So if you don't care about DFT, you can pay attention to the odd number ones. If you care about DFT, then you will probably be more interested in the even number parts of this. So if you sort of get lost in any of the DFT fun in 2 or 4, it's okay. Don't worry, we'll come back, and though some of these more general points should still be interesting. So what is symbolic regression? So a lot of what's going on in modern machine learning looks like this thing over here on the right. So this is a network architecture diagram. You got a lot of different things going on. There's many, many, many parameters in there. And the process of training is finding many, many things like what you see over there. Now, contrast that to the expression we have over on the left, and bonus points if you recognize this expression. But this is from material science, and it's kind of a rule of thumb expression, which is kind of useful. And it basically has three quantities about your system and 1 parameter. That's the square root of 2, right? That is a very, very small model describing, which actually does not a terrible job describing what happens for a particular physical system. These are such different things. And we as humans really like to think about the one on the left, and we can often reason about these kind of things in ways that you just fundamentally cannot do with these things on the right. And so if you've known me for more than a small enough time, you've probably heard me talk about symbolic regression. That is basically a set of machine learning methods to try to find things that look like those expressions on the left rather than the thing on the right. And it's gone on, there's been a lot of symbolic regression over time. It's never been like the most popular thing in ML, but it is something that does have a long tradition. And so I'm going to explain our approach to this through this talk. So first off, one of the conceptual things is rather than thinking about a symbolic expression as an expression like a parse tree or something like this, we think about it as a computer program. And so what we have here is the program over here on the left, these things we're going to call features are basically the inputs to the expression. Then we're going to have variables that get set throughout the computer program. And then there'll be some parameters which are going to be constants that we will figure out the right value for at the end of this whole thing. And in this way, this looks very much like a computer program, and you can map it back into a mathematical expression. Now, the nice thing is you can get things like, compute a value, store it, and then use it in several different ways later. And this actually happens a lot especially in physical systems, there's sort of intermediate quantities, and these computer programs very naturally represent that kind of idea compared to something if you did just a parse tree on a symbolic expression. So we're using the kind of framework of how this is represented that came from a paper on AutoML, which is basically a version of sort of finding the right architecture and other parameters for a very big model. But we're taking those same ideas and using it here as well. So from there, you can translate from this program over to a mathematical expression. Now, one thing actually I didn't actually fully realize until we started this work, there was this really famous paper by Schmidt and Lipson on symbolic regression back in 2009. But actually buried in the supplemental, they actually use something that is actually a program-like representation. This looks very much like machine code where they have load and multiply and subtract and so on. But it actually used this form. And I think there's actually a really good reason for it, is that when you have a symbolic expression and you want to manipulate it in some way, every change tends to matter a lot, right? You change, a power over here, you change part of the expression, you sort of comes out in the output. In a program, you can have lots of statements hanging around that aren't doing anything, that are there to be mutated and used later on. It's kind of like, we have a bunch of stuff in our bodies that isn't really being used, but is there for evolution to grab onto later and take advantage of. And that's actually, I think, an advantage of this computer program representation, because you can have these extra lines compared to a more traditional symbolic representation of just the equation. So how do we do this? Well, we do what is a fairly basic thing. Say, okay, what operations can we have in our program? So we've got, the first four, completely unsurprising here: addition, subtraction, multiplication, division. You're going to need those to make anything. We also did an add multiply, which you see a lot in programming languages and also really has just tended to be very useful. So we threw that one in. We threw in a couple of powers and we limited the number of powers that you could use. We can debate how important that one was. And then we have this last thing, which is probably going to look very surprising. This is basically inspired by what we saw in other DFT functionals using this kind of finite domain transform down here at the end. Now, I will say we actually tried putting in other building blocks of DFT functionals later on, and none of them were very useful except for this one. So I don't know what that means, but we will debate more of that in a few minutes. So those are that is what our program is made out of, right? No trigonometry, by the way, here. In other symbolic systems, people have needed trigonometry. You don't see it in DFT, so we left all that stuff out. So now that you have a program, you have some operations, how do you go from one program to another? Because the whole game here is searching through programs. So the set of operations we allow are basically, we can start with the program and we can add a brand new instruction. So here we are saying, okay, I'm now going to add an instruction which sets this variable v0 to the constant c1 times the current value for v0. So you can add and remove instructions. Then we have these change instructions. So you start with something here that's a plus and you convert it to divides. Now, one interesting thing here you can do is that some expressions like plus need two things in them. Some, like a power, only need one. And so as doing this, you can end up just dropping off variables along the way. But it's a perfectly reasonable mutation. And the last one you need is just to be able to change one of the arguments. So here I'm multiplying c2 times v1, and I change the c2 to v0. So with this, these are all the ways that we are going to be able to mutate programs.
Just to be clear, you have these sort of registers, v1, v2, etc., which are temporary in some sense, right? And then the c's are the constants.
Yes, that's right. Yep, so I will use parameters is the word I'll usually use for those c's. And the idea is that when I write the program, I don't know what they are. Eventually, I'll figure out the value and I'll set them to that. I'm going to explain that part. Yeah.
I'm surprised you don't use cosines and sines and stuff like that, because it seems in quantum mechanics that's sort of an important operation.
Not typical. I've not seen much of it in functionals, and so the sort of in the family we didn't have them, and so we didn't put them in. Now, I think it's actually an interesting question. If I put them in, would they be useful? I don't know, right? And this is actually one of my meta issues with symbolic regression that I will delve into a little bit at the end.
They're hard to make, right?
No, but because of continuous fractions, right? You can make any function very well with just division.
You need a scalar expansion of some kind, or
no, continuous fraction expansion. That's the fastest thing that converges, and then he has that.
Yeah, except we have a problem. There is one problem here, which is I'm actually limiting my number of variables quite a bit. And so I have with a very small number of registers, I think it make it hard to. Oh, but I think you could. Well, you might be able to do it with a few lines. So
for cosine and stuff, you don't need much. Actually, it's amazing how good the rational expression is.
But this is where these kind of things, we have these conceptual things like, oh, these are kind of the same. But then you put it in here and say, okay, it's easier to find a program that's 10 steps long than 20 steps long. Right? And so this question of which operations do I put in that sort of say what programs can I express in 10 lines versus 20 actually might matter a lot, but in really funny ways that we don't understand. Right? And this is, again, one of the, I think the complexities of this, we don't quite understand the kind of the inductive biases we're putting in when we choose to put cosine or not, knowing that often we can go back and get to something approximate.
So
Let me go to a test real quick, and then I'll come over, Frank.
I hope I'm not anticipating something too quickly, but I'm a little bit surprised that one might not consider derivatives as important symbolic things to include.
So we are going to end up putting in, so the features here are going to end up being like density and the gradient of the density and so on.
Okay, so you do that as
yes.
you kind of feature as the input with the gradient rather than putting them in the symbolic.
Yeah, and when we get into the symbolic form of DFT, then it'll become, that part will become more clear.
So are you trying to learn the density function?
Yep.
And are you using like an atom-centered or a plane wave?
For all of these, that's a good question. So this is we're using the data set that was used to make the WB97 family functionals. I don't know which one of those are plane wave and which one are atom centered because it's actually over many different problems, and they're all different. So I actually don't know off the top of my head what we're doing for that set. I'll explain the data set in a second.
For plane waves, I would think those antennas are probably very useful.
Yeah.
And for atom-centered, probably like distances would be very useful, which you can express, but it takes a couple of steps.
But you don't need them for the density. You don't need the distances. So, when I break down the functional, I think that part will be more obvious. Yeah.
And super quick, the insert, is it always adding at the end, or you can insert in some random spot?
You can insert in any random spot. So that way you can do things like, I'm going to add in this intermediate value I'm going to compute, mess around with the intermediate value, and then later on decide to use it somewhere. So you can get those kinds of mutations. Okay, so let's talk about the parameter optimization part. So here, this is an expression that we had that we come up with at one point. So all those C's and the gammas are constants that we're going to use. So where do we get those? So at the end of all of this, I'm going to be trying to find a functional which actually accurately reproduces a bunch of data, right? A bunch of I know what the output of the calculation should be for that functional. So to say, how do I find the parameters that are the best parameters for this particular form? And so here we use this thing called CMA-ES. So to minimize on the training set, we try a few times, we initialize from a unit Gaussian, and because we know a lot here, we can actually do things like limit our parameters to the range, to a reasonable range. So if you haven't run to CMA-ES, this is an illustration of how this thing works. So the two boxes here are representing a function, and you're trying to find the minimum on this fairly complicated functional space. And if the video restarts, you'll see that sort of start from a point down over here in the middle, and those blue points are all the points it's exploring. And the nice thing about CMA-ES is it does this increasing the variance of what it samples. And so compared to a lot of other methods, it tends to spread out when it doesn't quite know what's going on before it then converges the sampling down when it finds a good spot. And so there are many different ways to do that. We found this to be effective for this particular problem. If you have strong opinions about how to do parameter statement, I would actually love to talk to you because this is still that one worked for this problem and I move on. So if you have a more fundamental way of thinking about this than me, that would be great.
Just one question. So often some of the parameters might, by physical constraints need to be, positive or negative. You didn't impose any of this.
Nope.
Just
because here we don't know what any of these parameters mean. They're just parameters in the functional. Right, and so we don't have any particular meaning attached to any of these parameters.
Right. Well, let's say something like the homogeneous electron gas part of the functional should converge to a limit and so on. So you don't use any of those.
We do because of the form. I'll show that in a second because we're going to work with enhancement factors. So that's going to preview the answer. It'll be an enhancement. We're fitting enhancement factors, not the entire function.
Can I ask a real quick? Yep. So a lot of these symbolic approaches, they do like evolutionary things for the discrete part, but then they use gradients for the continuous part. But you're specifically not using like gradient-based things.
Yep. Yep. Because in each of these, because we'd have to do the gradient of the entire DFT calculation, because we're trying to find the parameter that produces the correct output at the end of the whole calculation. So we could try to do that. I have done things where you can compute a gradient through the DFT calculation. We're not doing that here.
Oh, but the reason is because it's hard to get the gradient, not because you're opposed to, you think it's better.
Yeah, no, there's no philosophical objection. It's a practical one. Yeah. Okay, so then given all of this, I can now explain this regularized evolution system. And so Evolutionary algorithms are a very common way to do symbolic regression, and we are sort of another iteration on this that has a couple interesting differences from other things you might have seen. So how does this work? So first of all, we're going to start off over here on the left. We have some population of programs, some population of expressions, all with some fitness. And here the fitness is how well does that functional end up computing what we believe is the correct output for that system. And so a couple interesting things about the way this works. Rather than taking the most fit member of the population and letting them reproduce, there's a randomized process here where you take a random subset of everybody in the population and find the best one of that randomized subset. So this is basically allows you to get a little more randomization in which members of the population are going to be varied on. So that's this tournament step here is sort of picking a random subset and deciding which of those is best. From those, you go through, we take the program, we go through some mutation operation, and basically we just do a fixed set of probabilities of how the mutations are done. You could imagine could be much smarter in other ways, but we sort of set up a probability of various kinds of mutations and just run it. From that, we then have to go into that parameter optimization step, and this is where we use this training set of examples, saying these are the examples that we're going to use for the parameter fitting, and then we take a separate set of examples and use that to compute the fitness of this particular equation, and then back it goes into the population over here. Here's the other interesting thing this regularized evolution step does is very often people go through and you remove the least fit members of the population. That's not what this does. It removes the oldest. Right? And the idea is that if you have an expression which is good but can't be improved, can't be changed in any way, it ends up falling out of the population. And so it ends up rewarding expressions that you can make other ones nearby that are also good. I think that's important, but I can't actually demonstrate that to you. But that is one thing that is different than some other evolutionary algorithms you've probably seen. So that is the main flow the main flow of this. And again, this regularized evolution is not something we came up with this paper. We sort of borrowed this description from another paper in the AutoML world. So here's the last thing I think is interesting, kind of from a big picture perspective on the symbolic regression system. Very often in symbolic regression work, the task of evaluating the fitness of an expression is fairly easy. You're like, well, just run that equation and see if it matches the number. But here, every single one of these is a DFT calculation. Because we have to take that functional, go through a DFT calculation to compute whatever the actual observable is, which is typically a difference in absolute energies. And so the process of actually going through and evaluating those is actually quite expensive. And this is one of the, just from a software design point of view, this is something that ends up being very trivially parallelized because you have many different DFT calculations you want to do. And so we end up having this sort of architecture of one part of the system is maintaining the population, creating a bunch of work of doing all these DFT calculations, calculating fitness, going over to all of these workers who are going off and running these DFT calculations, and then go back and update the population. And so this is a case where I think this is an interestingly different step from a lot of what a lot of you have seen in symbolic regression, though I guess some of the PD work probably also has this property. Yeah.
So since it's expensive to do an evaluation, why not do something like Bayesian optimization rather than evolutionary strategies where it's basically you have to do many evaluations?
So I think, could we be, the idea would come down to, can we be smarter about picking the next part of the population rather than just doing random mutation steps? Quite possibly, but doing how to do this in where the sampling distribution is actually very difficult, I think, to come up with what you want that sampling distribution to be and to make a good prediction of the posterior. Because here, what is the value of adding a new operation? I don't know how you're going to come up with a good value of that posterior.
In some sense, that's it. A normal Bayesian optimization, it's like a continuous space, but you have some kind of covariance kernel about smoothness, but it seems like here it's more discrete, and the mutation rule is roughly like the equivalent of the kernel, right?
Oh, but you can do that, right? There's kernels on discrete spaces you can define.
Sure, but your notion of distance between this program and that program is pretty. Yeah, I just
you
mean
can define it. Yeah.
I'm just saying that I feel like the evolutionary rules that you give are roughly the equivalents of those, right? they're kind of giving you a notion of how close are these two random expressions.
But I think the covariance of the discrete space, I'm not sure we understand at all, right? If I have a functional that works pretty well and I add an instruction, what should I believe? Like, I change from one, I add one instruction to an existing program. What should my belief be over the value of that new program? Like, I don't know. I don't know if I could find a distance function that would even make I would have any belief corresponds to reality.
It was small, then you could,
Yeah.
if it's a small parameter in front of the new addition.
Well, but you don't know, right? This is the thing, like it's very hard to tell by looking at the program whether that was a small change or a big one.
Yeah, so I guess smoothness is the issue.
But you still have to, even though like the kernel gives you a guess of what the acquisition is going to be, but you still have to search through brute force basically, which the values is, right? So here you still have to do that.
Yeah,
Search
but if you have a surrogate, you can search way faster on a surrogate, right? That's the you don't have to do a DFT calculation for
Okay, I
every
agree with
surrogate.
that, yeah.
So could we combine this with fast surrogates of functionals? Yeah, that would be cool, right? And I think that could possibly be quite useful here. We also might be able to be a little smarter in how we did this. The one smart thing we did is it turns out a lot of the functionals are exactly the same numerically, right? Because you can do these things like add a value that doesn't do anything, right? Or you add in, you have an expression and you add a constant. It actually doesn't matter, right, typically. And so we did this, there's a little sort of thing this fingerprint server thing here at the end is just sort of saying if they numerically look to be the same in the range that we care about, they're the same, and you don't go and redo all the DFT calculations. So that's the one kind of fun little optimization. Okay, so let me talk about the DFT setup, and we started to get some questions in here, and Frank already talked about DFT, so I don't know if I need to go through why DFT is so great, but at the end of the day, the wave function is really big, the ground state density is much smaller, you can do a lot more things with this. And so the whole point is to find the description of the interaction of the particles in this ground state density. Now, the one thing let's ignore that. Okay, so I'm not going to. So here's the form of the functional we're going to use. Now, this gets to your point about how we have constrained this and what we're actually fitting. So at the end of the day, the functional is this functional of the total electron density P, and we're going to break it into these 4 terms. And the beauty is those first 3 terms of the kinetic energy, the energy due to the external potential, and the Hartree energy are all things where we have exact forms. So the only thing we're trying to find here is this last term. And now we're gonna break up the XC part of this into a non-local part and a semi-local part. We're using a very standard form with dispersion correction, which is the same as what's in the WB97 family for the non-local part. So now we're only gonna work on what's in this semi-local part. And here we're going to use something that came up briefly, I don't know, in Frank's talk, which is we're gonna use this idea of enhancement factors. So the idea is we start off with the LDA, the local density approximation, uniform electron gas approximation. And then what we're going to learn is basically the change from the local density approximation for exchange, same spin correlation, and opposite spin correlation. So at the end of the day, we're coming up with 3 forms. But what I want to highlight here for everyone is these just kind of, we're only modifying one part of this whole thing. Right? We've set up a whole lot of constraints of what this form actually has to look like, and we only are going to go down here and mess with these enhancements factors down here at the bottom. And so this is not sort of learning from absolutely nothing in any case. We have a very constrained form. And so here we're going to fit the inputs that we're going to use here are the density, this thing called the reduced density gradient, and this function of the kinetic energy density. So those are going to be the parameters that go into the equation that we're going to fit here. So we did all of this on this thing called the MGCD B84 dataset, which is the dataset that was used to create the WB97 family of functionals. And so they did a lot of really good kind of curation work to get 84 separate data sets with about 5,000 data points of what a functional should be able to produce. So this is what, if a DFT functional is working well, it should do a good job across the wide range of these. These are slightly different kinds of problems, different kinds of inputs, et cetera. And they did some careful weighting because there's different sized data sets and so on. So there's a lot of details about how that was all done. We were basically taking the same set of things that came from that data set.
And so the functional you're learning is the local density approximation, basically, or could you do non-local things with your?
So it has a non-local term because of this dispersion correction, but we're just using this sort of standard thing that was already there. So this is a semi-local functional in that it has the density and the density gradient inside this reduced density gradient and this kinetic energy density. So we have, it is semi-local in the sense that it's using all of those gradients as well. And so that's why it's in this meta GGA class. So because it has the kinetic energy density in there also.
But the programs that you're learning cannot delocalize. It's just they're operating in these local density
yes.
coefficients.
Yes, that's correct. Right. And so now on the other hand, the final thing has this non-local part, right? But again, this is one of the maybe interesting. I'll highlight a point I want to make at the very end that this is kind of we are in an interesting constrained space of what we're searching for here. Okay. So does it work? So let me now present a few empirical experiments for this to show that the system I described earlier and the constraints we've talked about are able to find interesting functionals. So the first was just it was really a proof of concept that the system works, which is there was this WB97 functional, the B97 functional. Can we find it? So if we started off not knowing anything, right? And we said, so your original program is 0, it just outputs 0 everywhere. Can we go back and find the B97 functional? Now for this just proof of concept, we basically said your output is trying to recreate, we'll just give it exactly the B97 functional, so not the final actual calculation of the DFT result on that data set, just can you just reproduce exactly the values of the B97? So this is really just a validation that regularized evolution, symbolic regression system is able to do something. And so the form here, this right here is the form of the B97 functional. So the x is the x squared here is the input, gamma is a parameter, c is a parameter, all three of those c's are parameters. And so I'm going to show some plots that look a lot like the one that I've got up here. So basically, we're counting the progress of the evolution going from left to right here, just in terms of the number of mutations that we've done. The gray dots are the values for various functionals that we have along the way, and we use this blue area to show progress over time. It's the best functional found so far is in that blue area. And so basically down here at just under 4,000 operations, we find something which is this form here, which if you do just expand the squares and move around your constants, it's exactly the same as this one with different constants, and we fit exactly the right constants using the CMAES. So basically this says that symbolic regression system that I showed you, it can find a form. The regularized evolution does work when I have a sort of a fairly simple problem for it to rediscover. So now let's talk about the real thing. So now we are going to try to improve on an existing functional, which is this WB97 M-V functional. So should explain a little bit of where this functional came from. So we have this big data set. And they basically said, okay, I'm going to have a functional which is the following form. It's going to have some set of the terms which are just this expansion of powers of W and U, and it's going to fit these constants. So they had a particular way of picking a subset of those terms and then fitting those constants. So this is very much in spirit with what we're doing here. They just had a quite different method, and they basically fixed the form and just picked a subset of terms to actually use. But the B97 functional all has this form. And if you remember, we have these 3 enhancement factors for exchange and the 2 correlation terms. And so they end up with this, this functional has 3 parameters for the exchange, and then 5, and then 6 for the other correlation terms. So that was the kind of scale of function that we were talking about before, and it's just as sort of a proof of concept where I talked about writing these things as programs. This is just writing this form as the program that we have. So we can start off and say, okay, I'm going to start with the program that is WB97M-V for each of these forms, and I'm going to let the thing run. So what happens? So one thing that's different in the way we set this up, we did a bunch of evolutions in parallel. So in addition to having one population running and running, we just decided, well, we've got lots of machines. I was at Google at the time. We had lots of machines. So we just ran a bunch of them all together. I think this one was 12 we ran simultaneously. And so what we see here is, again, the number of mutations going over here to the right, and the best functional found, and we had around mutation 6,000, we get to this thing that we are going to call the GAS22 functional. And what is shown on the bottom here, if you just look at the top and the bottom row for a second here, on the test set, which is the values never seen during the training process. So we use the training set and the validation during the evolutionary process. And then we go through on this test set that was defined in the earlier paper. You can see we get a significant improvement in this weighted RMSD in kcal per units, kcal per mole units on the test set in this GAS22 functional. Right, so this is what we were trying to do, right? Get to a functional which on the same data set which produced that one before, we have something that performs better.
Is there any reason that you would expect that this approach versus the previous thing is going to generalize better?
I would say there's no fundamental reason to think this would be better or worse. This is sort of, we're allowing a more variety in functional form and have a particular way to search that space, where they were using these sort of, basically linear models along the way and use that to sort of, filter out terms. I think this would be more functional. I mean, it will tend to search the space of functions better. Does that mean it will find functions that don't generalize? I don't know. Right? It's hard to know how that would work.
Yeah. Another question: the energies to reference energies, where do they come from? Some high-level theory calculations?
So there are a bunch of different let me go back. Okay, there's a bunch of different types of problems in here, and so some of them are like the energy for separating two atoms and putting them together, right? That energy difference of dimer formation, and if I remember right, those are from just higher, some form of higher level calculations. Mm-hmm. I don't know for all of the. I think some of these are also experimental, based on. But I'd have to go back through to remember all the details.
So we trust those numbers. Basically, it's so better scores are probably better functionals.
I would think so. I'm sure there's a limit where at some point you're overfitting to vagaries of what's going on here. One thing that's nice about this, they did, there's a bunch of different kinds of data sets in here, and so you can see the performance for different kinds of data, and this is where we actually do see one interesting effect here, right? And so there's a question of they're all DFT calculations, but they're all getting to slightly different kinds of problems. So there's one technical detail I've completely swept under the rug, and I'm now going to explain. Which is normally when you're doing a DFT calculation, you go through a self-consistent field set. And that basically ensures that your density is what your DFT functional would say, and you're not just computing the energy of the, it's not just the energy of the density that we start with. So in order to make this whole thing go faster, we don't do self-consistent field calculations during the training. And the assumption here is that, okay, we had, there's been a kind of empirical observation that the densities aren't changing that much as we get various kinds of improved functionals, even though the energy estimates are. And so there was a little bit of, frankly, just hope that this was going to work out, that if we didn't actually do the self-consistent field calculations. But what we did is at the end, once we had our final functional, we did all that. We did all of the calculations for the final test in a self-consistent field, and the short version is everything is very similar, which means the functional does successfully, work in a self-consistent field calculation, though that is not something that is like fundamental to the underlying search process.
Where do you get your initial density?
From the WB97M-V, which is also the functional that we started for this one. So we just take the densities from that functional and use it here.
So I notice here that the first results for a functional is for this TCD, which I think are non-covalent interactions in dimers. If you have this table.
Yes, that is what they call it's the difficult set of the
set of non-covalent.
Right.
So it seems that in your optimization, so these are Decay interactions, right? So
thermodynamics. TCD is thermodynamics.
Thermochemistry, yeah. Can you go again maybe to this test?
Yeah, that was a thermokinetic. Yeah, I'll have to. I apologize. I don't remember more what that. Right. So it's these guys. Yeah. So you're seeing just maybe let me just point out something on that plot that you're seeing, just so everyone sees it, and we'll come back to this, which is what we see is that. So these are RMSDs. So down is better, and what we can see is we outperform the functional we started with, except for this, TCD set. This, difficult thermochemistry set is the one where this functional does not outperform what we started from. So yeah, I just wanted to give that context for the question here.
Yeah, that's fine.
But could it be that it's trading this off and that it's actually not better in some sense, right? That's the hard case, which is heavily weighted. It's not.
Yeah, so there is this weighting that we started from, because some of these are, and the weights are a little bit of like intuition of what's important, what's difficult. There's a lot goes into this weighted RMSD, and so it is the functional basically making some trade-off and like saying, it's okay, I'll let those go up so that I can get these other ones better. I think so, and this is where maybe now jump to like my kind of big picture thoughts. As we were hoping. And one reason I really like this data set is you would like to see it if you had something that outperformed consistently on all the different kinds of problems, right? But if it's like, well, it's better here and worse there, that's like every other functional that's out there already, right? Is like, well, you only use it on these problems and not those problems, right? And so we maybe, didn't get it, I would have liked to have something that was better and had less of that, expert knowledge about whether it's worth using. But we did, even for, so this one over here is just the test set molecules that were never seen during training. And you see even there for all these we're either slightly better or except for this one TCD, and the TC is very close as well. So yeah.
This question can wait for the reflections, but I'm kind of curious, like if let's say you want to achieve comparable. Like absolute error, but then like weight the different sections. Do the trends in the parameters, if you are to like fix the different symbols, tell you something about what type of term you would actually want to replace those constants with? If that wasn't too convoluted.
Can we? So here, let me go meta for a second here, which is one of the reasons I like symbolic regressions is now you can go in and understand in more detail what's there and what's not. And therefore, what might be missing, right? Where is this term? Where is the term weighted? And I will explain one of those in a second. But that's actually part of the point here is that you can go back in a reasonable way and understand what's going on here in a way that you can't in a lot of other cases.
So I have a question.
Yep.
If you use a neural network, how close can you go instead of a symbolic regression?
So
as a control.
Yeah, so I have not done it on this data set. So we fit neural network based functionals for other things, but I've not, I mean, I'm guessing someone has done it on this data set. I actually don't know of it using the same sort of trained validation test that was set up before. But that would be.
You can reduce the error quite a bit.
What's that?
I guess you can reduce the error quite a bit.
Possibly. Yeah, I mean, it's not, I could believe that and I could believe not. So
these are pine cones, don't worry.
Those are big pine cones. Okay. So let me show where this functional actually is different, than the WB97, and that'll get to one of the things. So, but this is it. So all that work, right? I can actually show the entire model on this one slide. You could take a picture and you could retype it into your computer and it would be done. You can't do that with a neural network as an aside, right? Right. But this is it. This is the whole thing that came out of this. So a couple things here. One is the enhancement factor on exchange is very, very similar to what we started with. So the machine did not end up exploring this. The form for the same spin correlation, this actually, you may remember, was this kind of expansion of the various powers of W and U. And we got something which is very much in that form. We picked a different combination than they did. So they don't have the 4-6 term, I think. I can't remember off the top of my head exactly which ones, but we picked different terms with different weights. But we're sort of in the same, it fits in well. And then the opposite spin correlation, the kind of funny thing that showed up is this, we have this thing to the 2/3 power that doesn't exist in any other functional that we're aware of. And so we have this new term combining the function of the kinetic energy and the reduced density gradient. And so this is just a form of this combination that is not observed in another functional and appears to work well. So it found something, you're like, wow, you found a cube root. That's really exciting. Like, is that, but it is, it shows that there is another form that people haven't looked at that is effective.
So the square root of x squared?
It's a cube root of x squared, so it's x to the 2.
Cube. Okay.
Yep.
The formatting is a little.
Is this dimensionally correct?
So that's another
You
good
have this
point.
W of a different.
A lot of these we end up doing transformation into unitless units, so that you don't have to worry so much about the unit. These things. A lot of these things you transform so that they're unitless, so that you don't have to worry about all of this stuff. Because there's other symbolic regressions that do a really good job handling that. In this problem, you don't have to worry about it as much because of the form we put it in. Let me just look at time. Okay, let me just say 2 things here. So now, if you're curious, how is this functional different than where we started? So there's several things going on in this plot. Let me not explain all the details of the plot. I'm just going to highlight the things that are different. So the important thing is that the gray lines here are the functional we started with, and the colored lines are the gas22 functional. If we just focus on that right-hand column in a couple different places. So this is one way of kind of viewing what is the functional. And so the things that we are seeing here, if we first look at the little places I've noted with pink here. So these are places where we have very low density gradient. So the density is very flat. And here we tend to have lower enhancement factor than what the functional we started with is. So that's sort of one regime where we see different behaviors when there's a low density gradient. And then the other one that's kind of noticeable is up here for weakly interacting systems. So these are kind of very, imagine very weak bonds or things that are sort of not that close to each other. And low density, we have quite a bit higher factor. Now, I will leave it for other people to argue what this means, what systems this should be important. But I think this comes down to, again, because it's a fairly simple function at the end of the day, we can do this kind of reasoning now and say, what systems is that going to be different? Where do we think we're going to be in this weak interaction and low density, and start to do more analysis of what's going on? Okay, let me take the last couple minutes here to just kind of reflect on symbolic regression and what all of this means. So first off, this is maybe a very general point that there's a lot of things going out in the world about AI discovered X, AI discovered Y, and it actually kind of annoys me. Because the fact of the matter is, all of these methods that we have here, we do a lot to aim the method very, very carefully at a problem. If you look at all the things we did here, say, okay, we're going to use LDA, we're going to use an enhancement factor, I'm going to put that term in, I'm only going to give you these things to work with. There's a lot of human involvement in an AI discovered thing, and it's true for every problem I've seen, right? And that I think we should be I actually think the language about how we talk about machine learning and other kinds of AI and general discovered things needs to really do a better job appreciating the the partnership that exists here between the humans kind of aiming and setting the problem up and then letting the machine go. So I think as just a general point as we talk about this. And the last thing is, the thing that has always bothered me about evolutionary algorithms is, boy, they always seem very specialized to each thing, right? I mean, nobody talks about evolutionary algorithm, right? No one says there's not a single evolutionary algorithm. They're always algorithms, right? And the reason is everyone is different. You can see all the crazy things that we did here, like, oh, well, we did the tournament like this, but we only have these operations and not at those operations. We were talking about cosine and so on. And it's kind of unsatisfying, right? It's like I have this something where I made all these choices about how this tool should work, and it's not clear how important all of those were. So we should acknowledge both the human and machine parts of this. The second is, if I compare Deep Blue to AlphaGo, right? If you remember, Deep Blue was IBM's test playing machine. Really, what it was good at, it was doing a lot of positions. Right? It was really it felt really brute force. And I think a lot of people in the AI world were dissatisfied at the end of it, because you're like, you could solve that with brute force? Like, it was like, I thought it was going to be like more interesting than that. But it turned out, like, if you just look at enough positions. Now, I don't want to give it too hard a time. There actually was a lot of smarts in there. There's board position evaluation. There's other things in there, but it really felt very brute forcey. And this feels quite different than what we got with AlphaGo, where there's still, there's some amount of it in there, but it felt like it had learned much more about the game in some way that is different than Deep Blue. Symbolic regression still feels like the one on the left to me. All right, if you look at what's going on, what were we able to do? We were able to try a lot of functions. And they're really coming to maybe to Max's point, we weren't really very smart about which functions to try. Not like we learned something about about these terms that, ooh, I really like that 2/3 term. Let's use that more. Nope, we're just like, throw a number in there, throw a new variable, throw a new parameter. So I'm kind of unsatisfied in this way. Like, it feels not intelligent in the way that I would like for it to be. And there were a lot of interesting things that we didn't really get to, right? Which is, we mentioned earlier that we got this SCF convergence, the self-consistent field convergence. I don't know if we were just lucky, frankly, right? Like, it totally could have ended up, we found a great looking functional, and then we actually run it, and the whole thing diverges, gets to a different density. It could have been a disaster, and it wasn't. So did we just get lucky? Maybe. Did the fact that we constrained the form so much mean that it was going to work out? I don't know. I have no idea. Yeah.
I think it's a common finding too. I think the DeepMind functionals are the same thing. And I think that there's a lot of benchmarks where you compare different functionals on the same density.
Yep.
Like, the vast majority of the difference comes from the functional, not the density.
Yep.
So I think it's more than just this. I think it is something that people tend to accept.
And maybe it's just a property of the DFT world that our densities are good enough at this point.
I think so. Yeah. Except for some cases where they're definitely not.
Right.
But I think a lot of the time they seem to be, yeah.
Yeah, and I'm actually worried about those cases where if it's right on average, right? But the ones where it's wrong are actually really interesting, right?
Exactly.
Like, we should try to work on
And I think part of the interesting thing about the DeepMind functional too was that the ones where it did better were these cases where electrons were incorrectly delocalized. So they used the wrong density, the wrong delocalization, but the functional was still able to fix the delocalization to an extent. So there are those cases where it's wrong. But
interesting.
yeah.
There are definitely functional examples in the sort of language, something which give you completely unphysical density stuff.
Okay. But I think there's a question of, like, why didn't we end up in that place, right? And we happened not to here, right? And so, like, I feel like we probably could have, right? And we didn't, right? Now, why? I don't know, right? I think it would be a very interesting exploration to know if, were there many functionals that we explored that would fail this SCF kind of test? I don't know.
So, but isn't orbital-free DFT precisely that? You don't do the SCF. I think the problem is that you might search in a space of densities that are not representable by any wave function. And so you might find something that's actually not physical because of that reason. And so the Kohn-Sham, so maybe I misunderstand, but you're skipping the Kohn-Sham equations, basically.
No, we are using the Kohn-Sham equations.
I see.
Right, so way back, when I broke up the functional form, this guy was in Kohn-Sham DFT. So especially like the kinetic energy functional, that all comes from a Kohn-Sham setup. So that's why we need to do this self-consistent calculation.
Okay.
Yeah.
Have you ever tried, if you were to go back and not assume that there's the kinetic energy or the external potential that you would recover those?
Yeah, so maybe I'll use this to make this last point on this slide, right? Which is, we made many choices here, like, okay, let's just use those fixed forms, let's use the existing non-local. And you asked this very reasonable question, like, well, what if you had done it this other perfectly reasonable way, right? And I've been really struck by, and how much of the science we do, there's a bunch of reasonable choices that we make, and rarely do we understand the effect of that reasonable set of choices on the final outcome. And there are these two papers up here, which I'm betting nobody else has read. They're from the social sciences. And they basically they do this really just beautifully executed experiment where they get many teams of analysts together to try to answer the same question from the same data set. And they have them peer review each other's methods, right? They go back and forth, but they sort of review the methods before the results are known, and all of this. And it's just a beautifully executed thing in the social sciences. I won't go into it. And they show how much, like, even among methods that look perfectly reasonable among peers, they can get quite different outcomes for the same analysis. Now, this is a world where they have a fixed data set, and it's one of the problems with social science, but it just really lays bare the impact of those choices of things like these things we were just talking about. The fact that I constrained the form in the following way. If I had put cosine in there, what would have happened, right? Would I have found something better? I don't know, right? And it's just, I do not think we put enough, that we have quite enough appreciation for the potential impact of all of those very reasonable choices, and I think we as a scientific community need to figure out a better way to deal with that. And so this is all interest you. I highly encourage you to read those two papers, even if social science papers are not usually your thing. So had lots of questions. One thing I do want to point out, this functional is now part of libxc, which means it is probably now in your DFT code of choice. So if you would like to use it, you can go and use it now, and I would love to hear any experiences that you all have with it. The other thing is, I'm the one standing up here, but really all the hard work was done by Lee, and Arun, and it's actually kind of when we were preparing for this talk together, we realized we're all, the research group we were in, we've all gone elsewhere now. And so nobody is still in that research group anymore. It was a bit of a moment of nostalgia. So, but thank you all very much. Happy to take more questions.